what I was saying, I had to do, like we are doing now. We didn't have that much funding or anything, but we had fair amount. Professor had, he was in Germany with, the famous people, Wagner and all those people. He was my professor. So you mean
Okay.
at Max Planck, So
Right.
he had good connection, and I met a lot of top people from England.
Wow.
Professor Parkins, Lucas. So all those people, they used to come and see me in my office, and we had good relationship. And I could present it. So everything was going well. And then, so for this one, I didn't do much IT. I knew Fortran because that's a studied. Even my that's why I told you about the Fortran. I did my bachelor in India.
Oh,
Yeah, that's the one time I studied. It's a self-study.
yeah.
There was a book, somebody from India, he has written a book. So I studied. I said, I'm going to try it. You know what I tried on? Magic Square.
Oh,
I was so
great.
interested in that. So I programmed it. It's very nice. It was a punch machine, that time.
Yeah.
And so I had to use punch machine. But I used to submit as, it's called job B, submit. And they were very impressed. So I used to, the first time itself, I did fairly well with the programming Fortran. And
Right.
I had a nice algorithm to generate 3 by 2 by 2, 3 by 3, 4 by 4 magic squares. It's a very simple formula, right? You just everything has to add up, but you have
Yeah.
to have a loop that
Yeah.
goes and then checks everything. So I put
It's a
that loop
nice,
in
it's a good starting sort of algorithm, I think.
algorithm. Yeah. So it was
Yeah.
very successful. I'm sure IBM or somebody used it. My thing, but they, many of these things they use it, but they don't give me credit. But it was a really good one because I really got output. I tried few times. There were some bugs, but after a few tries, it was churning out answers.
Right.
The correct
And
answers, and I checked with them with my calculator. It was working well up to like I think it goes exponentially very very high. We
yes.
got up to 10 by 10. It's very large. It's huge
Yeah.
even for the computer. But it was
Absolutely.
turning about that much. I know definitely more than 5 by 5. I easily got 6 by 6.
Yeah.
So
And
that
so,
was good. So with that, I did the finite element modeling, Newton-Raphson method, trial and error. And again, I did a very small algorithm, very nice, very efficient algorithm.
yeah.
And initially what happened was my algorithm was so efficient in that even the Penn State, it was not punch machine, but it was an older IBM machine at Penn State in the 80s.
Okay.
Older, but the late 80s. And I punched that in that again, the Penn State also, they were quite interested. And the algorithm I did, it was so efficient that it was too fast. So it was churning out some, I checked with my calculator, it was churning out some garbage. So I checked that. Finally, I figured out the time delay. That's the first thing. So I did the fundamental research, fundamental finding on the IT itself.
Yes.
Computer. Until then I thought, oh, computer, you can churn out. That's not certainly true. You have to put a time delay. Actually, they're using that time delay, even IBM. They don't give me credit, but I think I was one of the first ones to really realize that. Essentially, what happened was I found out time delay. So I put a fictitious time delay. So it'll go that, and it was started working beautifully. Because it was a short program, highly efficient program. But then I did a small student test. I didn't use any other packages. Student I had some course, so I used that. So it was quite efficient, and we could get results, and enough to publish. Uh, so really, that's a modeling I had. So I can understand what trial and error, what they're talking about. My physics was my high school days. Einstein thing was very attractive to me, but it was very hard uh, for me to, it's too much complex math. I didn't go in that direction. I wanted to, but eventually I did engineering. So there is not that much. There is some math, but I thought that for the quantum physics and relativity physics, although it is highly, now people are doing a lot of math. you know.
Right.
Yeah, just math. But the physics is not there. So they're finding, like you have said, they are finding a lot of odds. They are not finding consistency. It's not the CPT problem, the charge polarity, the parity, and the time reversal problem. They are not able to solve. And the antimatter matter problem, you know, we still have not resolved that. How there could be more matter than antimatter. And our paper actually hints at that. You see that? You saw the Susi. See, the formalism with Marco is, I find that the most powerful because the vortex field and the gradient field, we are able to do at the point level. And the problem solving, I define that it shows nice figures which shows the variation. See, it has to show the variation, why there is a variation, and it automatically shows that when the vortex, the gradient field is affecting the vortex, it's a natural thing. It's a Helmholtz from the Helmholtz decomposition.
Right.
It's affecting the whole thing. It is making it asymmetric. So I feel that, and that's something you may also work on. The way I look at it, very simple model is that what is happening is that, and right now I'm working with another guy called Emery Trailer, and he's working on a falsification of Einstein thing. I'm not that much. I told him not to emphasize too much on that, but we'll see. But there I'm developing some new things. Gauge, using gauge. So gauge theory. So he thinks that it's a discontinuum. So there's a discontinuum at that level, and then you have gaps in there. So the one point to another, there is a gap. And this discontinuum length is constant. So if you apply the gauge, which is differential, it automatically cancels out. And then all you have to find is count the gaps between the two things. What is happening is that why there's a cutoff is that at a higher level, you have dipoles forming and also the positron and electron colliding. So what happens is it creates, I want to make it a little simpler and we will expand on it. What happens from the circuit, either the positron and electron can annihilate each other, right? And when it annihilates, it pulls apart the North Pole and the South Pole. And that, I think, is the phonon. That becomes the phonon. That becomes the phonon.
But isn't a phonon like a sound particle? Or am I thinking of, what are you thinking of?
Yeah, what I'm thinking is that when the following mechanism, actually you will know a little more because that's why, this is an idea I have, but I think you would probably have better comment on that. You will, more technical aspects. What happens is there are two possibilities, like say two variants, right? One of them is the North Pole monopole and the South Polar pole will, because of the Gauss theorem, they try to form dipoles. And when they form dipoles, what happens is a dipole is a magnetic. Now it's magnetically aligned, so that becomes a photon. It immediately releases. It immediately releases from that wherever the location is, a photon. Okay? Right. The other variant is instead of the two, the North Pole and South Pole combining, is the electron and positron annihilate each other, and that pulls the North monopole and South monopole apart, and produces a high pressure. And I have calculated, like you might have seen that. I think recently I saw, and it gives me more confidence, 10 to the power 26 of metric unit, whatever the unit is. It's a very high level of energy is released. So it creates a high level pressure. That pressure wave is essentially a phonon.
Yes.
Okay. So it releases it's like a micro Big Bang or a blast. It's a heavy explosion because of the pressure. So what is happening is that at high levels, these are combined level, right? When you go to the quantum level, they are splitting into the circuit. They form this below the sub-quantum level. They are making into this circuitry, this monopole and particle circuitry. They keep revolving like a clock. like a clockwork. They keep going, right?
Yeah.
Until they create these processes, reactions of either forming, the phonon or photon, right? Now, what guides that? That's where a prime factorization comes in. So the fundamental mechanics of prime factorization, we have to find that I think mathematically you can prove that. So the prime factorization is that any composite, mathematically speaking, any composite number splits into prime numbers. And it is convenient for nature to do that. We have to justify that mathematically as well as some physical aspect. I think from your crystal studies also, I think, it will prove. And then immediately as it forms a magic square type of thing. Like you mentioned, it tries to form magic square.
Okay.
And again, mathematically, you can prove that why it tries to form a magic square instead of a real symmetry, So magic square is not a very good symmetry, if you have mentioned. It's not a crystal symmetry. So what happens is the magic square is good, the transition thing. It stays there. It has fantastic properties of aligning the directions and all those things. But it's not a perfect thing. So what happens is it will try to create what we call a crystal symmetry or super crystal symmetry, super symmetry, or SUSY type thing. Like we are derived that from fundamentals. We didn't use anything but our Markowitz, myself, formalism, just from the simple analysis of vortex fields and gradient field, we have derived the SUSY, the supersymmetry matrix. So what happens is that, so it is forming that supersymmetry. For example, it will try to form that. That is a driving force, right? So the magic square cannot do that. So it will start producing rotational forces because the field, because asymmetric field, it will start make it to rotate. And I think we should be able to prove it, but geometrically, algebraically, and geometrically, those things. I think you have done a lot of those things, very similar on similar lines. You already have so many matrices of magic squares of different elements, including Higgs boson and all those. You analyzed all that, so it should be easier for you to do that. Once we get all this ironed out, we still have some bugs to iron out on this model, but I think this is a very good model we have to start on. So what happens is, so it tries to form that, but eventually it finds that it has odds and ends, right? It has a lot of these perforations or what you call edges and all those things, right? So it has to break it up. So what happens is it breaks it up. So it forms many fragmentation. We mentioned that in our paper. I mentioned that it tried to form fragments. So it will create fragmentation. That's why we have constellation. See, if you go there directly one-on-one relation, micro to macro, why there are constellations, so many constellations, and then if I form galaxies, it automatically follows. The micro level is a reflection of that. It's automatic symmetry, micro symmetry and macro symmetry. Right. So it fragments that, and that's why you see so many dimensions. Quantum level, people talk about 64 dimensions or even more. I don't know how many dimensions they have. Not infinity. It wouldn't make any sense to have infinite dimensions. That would be totally ridiculous.
I think so.
Yeah, from mathematical point, logically, it's illogical. You think, what is a dimension? The first place. How can you have infinite dimensions? No, there is no way. You can have large number of dimensions, yes, but it has that dimension. N has to be less than infinity for sure. You can logically prove that. But the whole. Yeah,
I don't think it would be useful mathematically, probably anyway, to be dealing on that level.
Yeah,
like from a physical perspective.
Yeah, string theory, superstring theory, they have so many dimensions for everything. But I believe in string theory. It's a good thing. Mathematically, it's a very pure thing. And I did the pure math. See, I did the pure math now on one level, right? From the matrix, we have proved already. Manuel and myself have published that in the proof formalism. It's a very simple matrix property used, and that derives that functional and all those things in our proof formalism. So that's a pure math. The other side, almost pure physics, is where our formalism with Markowitz comes. And our thing is applying, putting these two together nicely, and then coming out with your magic square and quantum level, and then Manuel's astrophysics. And then we have this circuit. I think that will be the most fundamental circuit. So what is happening is that, so it is fragmenting. So higher levels, what happens is then it's forming the photon and phonon. So now it has facility with that. Now we can use Feynman diagram and all to show that the photon will be a mediator, of the thing, and then see how we can. And I believe that our thing has much higher standard, my probability of grand unification than other things. And if we put together the prime factor, which, those arguments are a little tougher, but I think that's something we have to work on. Logically, we have to argue why nature decides to do a prime factorization. Why is nature doing that? What is the fundamental thing? There are equations like what is the Italian? He has done the numbers. Try to remember. He has said that 2 and then 4.
Fibonacci, is it?
Yeah, Fibonacci. Yeah. So Fibonacci sequence, for example. The another one about fractal theory and the other things, they said that if you rearrange the quadratic equation, right? X square plus, and then the solution of that, X square is X minus, and if you do that, a lot of the things follows that fractal thing.
That's right. You have the Pascal's triangle.
Pascal's triangle, and you are doing that quite a lot. So I think you are doing something similar.
I like those kind of connections.
Yeah.
I like to make sure that everything is connected as much as possible, so that I have a good, and then like try to find more connections.
Yeah.
And sort of, so I start very simply with like one concept, and then grow it until so that it's including things that I didn't think were going to even be included.
Yeah.
And then just grow it and make it more complicated, because so reality has to start kind of simply and then become more complicated.
Yeah.
So you were saying that, sometimes you don't understand where it's going. And I would say the same, like, I'm not entirely sure, like, when I began, I had no idea that I would be where I am. And even yesterday, I didn't know where I'd be today, kind of thing. But it's a good, as long as the progression is going, and, and like, even if I'm falsifying what I'm finding, that's okay as well.
Yeah,
so
sure. You are learning from it and you are improving. Now, I believe in that. See, initially, I had an idealization, so to say, of that. From young days, I had this intuition that if you do it right, all the pieces should fall into pieces, or fall into right pieces to develop the thing. Somehow I believe that the nature gives, you just have to, you will get these things, and you have to be objective and unbiased. You may get different things which will conflict each other, your own thing, but you continue working on it and you believe in yourself. It's a fundamental aspect of God and all, but the divine thing, somehow these pieces will come together, and automatically, I believe in that it has to do that. So then the nature is really telling you something very similar to the 10 Commandments the Moses had, very similar thing. And I believe in that. I have 11th commandment. I had a book called Absolute Genesis. And then we will, once you have the Hawaii conference or the other world conference, the North Pole or someplace, maybe a couple of years, I'll bring that book. At that time, I'll bring it, because in 97, I published that. 2000, it's published in Amazon.com. And it has the most fundamental thing. Even now, I find that it's useful, but you cannot argue. A signal is a function, it's a special function of noise. The noise becomes signal. But that function, what it is, and I am finding now there are three different aspects of function. Function, functional, and functor. And I believe in functor theory. Functor theory talks about different categories. If one point, it's a discontinuum, I think is very useful. Because one point is a functor to another point. which means they are disconnected, but they have categorical relationship. And what connects is the functional. Functional connects between the functor, and inside each point, for example, the function holds, like a wave function holds.
Oh, okay.
This is a very fundamental thing. I think we'll be able to prove. We'll have another paper after this paper is published. And eventually, I want to start the following way. After these 8 formalisms, we may have one more paper or something, another paper, manual, and then the other person also. We may have 1 or 2. After that, I'm going to start, and I'm already talking with one person in Uzbekistan, so part of Russia, and he has been good. The Davronovich, his name Jurav, Professor Jurav. You may have come across this thing, and we had some conversations. And he is now guest editor. So he said, "Yeah, I'm interested. You can send me." So the following, I want to start the following way. Something called theoretical experimental physics. This slide is eventually like 1,000 volumes. Okay, volume 1 will be essentially conjectures that we are coming up. So we will be outright. They are ideas, conjectures. They are not. You cannot expect more than that. There is no validation there. But they are not ideas. They are more than ideas. They're conjectures based on observations, which are fundamentally logically provable, and also theory, fundamental mechanics. So people can join that, and that will be one of the first volumes. The second volume will be modeling to quantify that, and then eventually theoretical validation, then experimental experiments about that. But I think the discontinuum physics we are doing, the other person, Emery Taylor, I think it will shed some more light, and you'll be able to put together all these together, quantum relativity or quantum gravity, so to say, and see. And I think we have a model is also coming together. The more difficult aspect, I think I have figured out. I mean, that was the hard thing. It was a brain hacking, mind ranging thing,
Yes.
It was really breaking me apart. It's make me go crazy. I think that aspect is gone now. Now we have something to base on. The formalism I had, that's the most fundamental. And our thing, once it comes, all you have to do is go to the next level. We don't have to worry, the circuit, I think, is the most fundamental circuit. And I believe that the smaller one, it breaks apart into the circuit, right? The monopole and the particle circuit, when it goes to the smaller level. The larger level, they combine and they form phonons, photons, thunder, lightning, and all those.
Sure.
And then if you can prove that micro-macro connection, I think we had it. We got it. We essentially connected the whole natural physics.
Yeah, because I was interested in creating a simulation of like thunder and lightning and stuff. I actually saw one on YouTube that was pretty good. And it basically works through breath for search. So, it searches through a labyrinth.
Yeah.
And then the first point that connects to the ground in the model, they just create a line through the labyrinth. And I thought that was a really good way of solving the problem. So I had a slightly different solution that was going to be more along the lines of it's kind of hard to put, but like it would be like a 4-dimensional model where you'd have like so you'd have a 3D volume like a cube, and then when you pull away the 4-dimensional cube, it would be like almost like a sticky substance that would so form a dendritic pattern. Like, have you ever used potato printing, where you squash paint and it forms like a dendritic pattern? That's kind of like the sparking of the lightning,
like a buckyball or what we call the fuzzy ball type.
The buckyball molecule. This would be more
and also like putties, or what would you call it?
Oh yeah, like so if you were to,
I was thinking about something very similar to what you're thinking about, how they of course we have the toroid, the shapes that interconnects to the 4 dimensions, toroids and things like that, and how they interconnect. I think probably you already had made models. I'm not that much into that, but probably you already how the cup becomes the donut or something like that.
Topology and all that. So but this thing, like where you were talking about, where you'd have I find it interesting, like the kind of localization of, like, you know, the way you're saying, like constellations, like things that group together. I always find that interesting when I was growing up, like philosophically thinking about it, like what determines the extent of an object? Why does an object extend infinitely? Like, why is it has some sort of boundary? And then, so this was kind of related to my concept of this electromagnetic thing that I'm looking into. You know, so you'd have the idea that it would like to extend forever, but there's a cohesion to it, and it zips back into itself. And it is the gaps that are just as important. I think I have about 60 papers on ResearchGate at the moment, something like that, close to 70. And the more recent ones I have, I've got, like, I'm kind of getting into parametric, what do you call them, graphs of the particles and the relationship to this thing, which is a bit like a permutahedron. It's like it's a bit like Garrett Lisi's E8 theory, but slightly, like, quite different as well. And so I'm making all of these graphs, and then at the moment I'm kind of working on more like eigenvectors. That kind of thing. So trying to get the characteristic polynomials and all of the particles, and then of all of the.
Is it Legendre? Are you using Legendre polynomials also? Legendre polynomials?
No, I'm not. I haven't gotten to that stage or anything yet, but I've come across it. But at the moment, I'm just using characteristic polynomials based on, like, the determinant and the trace and that kind of
characteristic equations.
Right, and I'm getting that from the 24 cell, and then because I've already mapped the particles onto that, I'm trying to link the two, and then, so like I did with the parametric equations, just to see, like, if there's any patterns there, and it's kind of coming along nicely. So, like, then I'll be able to work in the Lagrangian, and then finally, you know, or well, maybe not finally, but the ultimate goal here will be Schrodinger's kind of parametric equation.
So you have what I guess is you are doing a very thorough job.
Oh, thanks.
And more thorough than anybody I have seen, any other physicist seen. So I really impressed, and I think we have a successful team now to make a publication, because this publication should go on, will go on.